Hello everyone, welcome back. So in this episode we're going to talk about the relationship between dominance and best response. As you remember the definitions, there is a logical relationship between these two concepts, and this is exactly what we're going to talk about in this episode. So let's recall the definitions first. So the first definition is the dominance. So a strategy SI is called dominated if there exists some strategy, which is probably a mixed strategy, such that player I's payoff from playing this mixed strategy is greater than playing his strategy SI for every strategy profile belongs to his opponents. However, SI is called best response to a belief about the opponent's play if the player I's payoff is maximized when he plays SI. All right, so that's the relationship. These are the definitions of these two concepts. So, in order to formally describe, how these two definitions are related, let's define two concepts, two sets. So I'm going to call UDI as the set of all strategies of player I that are not strictly dominated. Okay? Meaning, find all strictly dominated strategies of player I, eliminate them, and look at the remaining strategies. So those strategies are not strictly dominated. So that's going to be so this UDI is basically a subset of S sub I. Okay? All right. Well, we are looking at the pure strategies here. All right. So the mixed strategies are not included in this UDI set. And BI is, let's call the set of strategies, set of all strategies of player I again, that are best responses. Okay, well, that's also a subset of SI, obviously, but these are restricted, sort of smaller subsets of set of strategies. So mathematically, we define BI as follows: SI in capital SI such that there exists some sigma minus I element of this set. So there's a belief about the opponent's play such that SI is a best response for player I to sigma minus I. All right? So that means there exists some belief for player I where SI is the best response to that belief. And so if that is true, well, that strategy is in this set BI. And a strategy is UDI if it is not strictly dominated. All right? So how are they related? Well, this is a theorem, in fact, but we're not going to prove it formally. We're just going to show that it is true through some examples. But the theorem is the following. I'm going to just state it informally. For two-player finite games, these two sets are actually equal for both players. Okay? So what does that mean? That means if a strategy is a best response, well, then that means it has to be, it can't be a strictly dominated. And if a strategy is not strictly dominated, well, then it must be a best response. Okay? So what do we mean by finite games? So the finite games are those that have finitely many actions, strategies. Okay? Pure strategies. The two-player, there's nothing complicated about this. Well, question is, can I extend this theorem to more than two players? No, we can't. I mean, we have to change the definitions of these sets slightly, but sort of technical change is important. But one thing that matters is that whenever a strategy is a best response, well, then that means that strategy can never be strictly dominated. All right? Meaning BI is subset of UDI for every I, even for finite games with more than 2 players. However, the converse is not always true. I mean, so let's suppose there is a strategy which is not dominated, but does that mean that, which is not strictly dominated, but does that mean that, I'm sorry, this strategy is a best response? Well, we can't say this, all right? Again, when we have more than 2 players. Okay, so here is one example that I would like to talk about. Oh, one thing is like, how do we really verify, BI is equal to UDI? Well, I mean, first off, look at the best response strategies for the simplest beliefs, where those beliefs are pure strategies. All right, so find best responses for pure strategies. Right? So don't look at mixed strategies, just look at the pure strategies of the opponents and then find the best responses. Well, that means if you find any such strategy, it's in BI, obviously, because it's a best response, but also it's in UDI. All right. What else? Well, you can find strategies that are dominated. So if a strategy is dominated, well, that means it's not in UDI and also it's not in BI, okay, automatically. And then sort of the third stage, well, you look at dominated strategies by considering mixed strategies. All right? I mean, maybe a pure strategy does not dominate it, but a mixed strategy may dominate it. So that's sort of relatively harder to do in comparison to the first two, but well, it's doable. And in fact, the next example, we have to follow all these 3 steps to figure out or verify that UDI and the BI sets are identical. All right, so here is the example I have. There are 2 players, and player 1 has 4 strategies. I'm going to call them A, B, C, D. Sorry. Player 2 has 2 strategies. I'm going to call them X, Y. And here are the payoffs. 3, 5, 3, 6, 3, 1, 8, 2. And what else? 7, 6, 2, 3. And then 6, 7, 4, 1. All right. So here, let's calculate the best responses. All right. So I'm going to find BI, B1. Let's focus on B1, and I'm going to also find UD1. All right. So the best response. So given that player 2 is playing X, what is the payoff maximizing strategy? It's C, right? Because it gives 7. So therefore, C is definitely in B1 set. Okay. Given that the second player is playing Y, the highest payoff is achieved by strategy B, so therefore B is also in this set. Well, the question is A and D are in this set? I can't say yes or no at this moment because all I looked is the pure strategies, all right? It's pure beliefs. Well, maybe a mixed strategy, a belief with some probability X, with some probability Y, well, then maybe A or maybe D is going to be best response, right? I can't know this. What I can know, however, I can do the following in order to find all best responses. And so let's do it. So let's suppose a belief is such that P probability X, and therefore the remaining probability, which is 1 minus P to Y. Well, in that case, what is the utility of player 1 if he plays A under the strategy sigma 2, where again, sigma 2 is this, P probability X, 1 minus P probability Y. So what is this expected utility? What is the expected utility if he plays B instead? And C, and finally D. I don't know why this U is different. Okay, so there's no specific reason. Well, what is the expected payoff if the second guy is playing P1 minus P probability? Well, then it's basically 3 times P plus 3 times 1 minus P. So if you do the math, it's going to be 3. Well, however, if he plays B, it's going to be 3P plus 8, 1 minus P. So if you just sum them up, you're going to get 8 minus 5P. What is this? Well, it's 7P plus 2, 1 minus P. So if you add them up, it's going to be 2 plus 5P. And then finally, this is 6P plus 4, 1 minus P. If you sum them up, you're going to get 4 plus 2P. All right? So obviously, except A, all the other actions, payoffs, will depend on the P value, which is fine. So what I can do next is a sort of a graph. So let's call this P, right? P can be 0 at least and 1 at most, right? So here is the payoff scale. So 0, 1, 2, 3, 4, 5, 6, 7. Oops, I wish I had 8 here. Okay, so utility of player 1's, it's just a straight line where the utility of player 1 is 1, right? Regardless of the value of P, the expected utility, expected payoff of playing A is going to give me the same payoff. All right. However, the payoff of playing B varies with P. I'm sorry, let me take it back. Payoff of playing B, expected payoff of playing B, varies with the value of P. And how does it vary? Well, so when P is 0, for example, the maximum can be 8. And when P is equal to 1, the minimum can be 3. So therefore, this is what expected payoff of B is. So this is B. This is A, right? So what you see here, expected payoff of B is always higher than expected payoff of A. So basically I can conclude A is strictly dominated by B. All right? So A is a dominated strategy. And well, okay, so good thing. Is it strict? No, unfortunately. Why is that? Well, because, you know, these two guys are equal to 3 at exactly P equals 1, meaning the second guy plays X. So therefore, I'm taking it back. I can't say A is dominated, strictly dominated. At least B does not strictly dominate A. Maybe something else. We'll see. Okay? All right. The next, what about the expected payoff of playing C? It's this guy, 2 plus 5P. So when P is 0, I know it's 2. All right. When P is equal to 1, this is 7. And therefore, so this is 7. Okay, look, all of those are straight lines, right? Linear lines. So for that reason, all I need is to find the endpoints and then connect them. That's it. So you don't really have to worry about it. Well, how they, I mean, at which point they're going to intersect, I don't know. Oops, I'm sorry. That's a horrible picturing. So let me try again. This time, just one straight line. Okay, well, hopefully this is a proper straight line. So this is what C is. So as you see, strategy C sometimes gives better payoff than A, sometimes worse. Same for B, so there's no strict domination between B, C. And then finally D. What is the what is the expected payoff of playing D? So once again, if P is 0, it's 4. And when P is 1, it's 6. So 6 is here. All right, so therefore, this is what D. So here, all these intersection points, I just draw them a bit randomly, to be honest. I don't know if it is above or if it is below. So it's important that you have to be careful. But one thing is kind of obvious from these pictures is that D is always giving me strictly higher payoff than A. So D is strictly dominated by A is strictly dominated by D. I mean, I didn't really have to draw all these. It's just kind of obvious when you look at those. So A is giving 3, D is giving 6, so D is better. A is giving 3, D is giving 4, so D is always better, regardless of what the second player does. So therefore, A is strictly dominated. So you know what? That means A should not be here. All right, A is not here. Very good, because it's strictly dominated. All right, I'm putting this X so that it's not included. Well, for the remaining ones, is there any sort of strict domination between B, C, and D? Well, maybe yes, maybe no. Let's check. So here, what makes the comparison between, for example, B and C. So here, if you remember, this was B, right? And this was C. So they clearly cross one another at some point. And so what does that mean? That means B cannot be dominated by C, C cannot be dominated by B. All right, so there's no domination between B and C. What about B and D, for example? All right, so here, once again, this is B, and D is this guy, all right? So this is D, all right? And this is B. And once again, B and D are intersecting at some point in between 0 and 1. That means sometimes B is better, sometimes D is better. So that means I can't say, for every strategy of the opponent, B or D is going to sort of make him better off. So there's no strict domination between B and D. Well, finally, what is C and D? All right? Well, this is C, this is D, and C and D, again, intersect at some point between 0 and 1. So therefore, there's no strict domination between C and D. All right, so that means the undominated strategies, the UD1, are everything except A. So B, C, and D. Well, what about the best responses? Well, do I really have the best responses? I mean, C and B are always best response, right? For example, when P is 0, clearly B is the best response. When P is 1, clearly C is best response. So here, D should be best response at some point. So that means if you look at, this region, when P is taking values in this region, you'll see that D, all right, is taking higher values than than B. So these are the values for B in this region. And then taking higher values than C. These are the values of C in this region. So therefore, C is in fact best response whenever P is in this range. Well, what is this range? We can double check. So that means B, C, and D are also in this set. We can double check and sort of give a specific value for P and show that it is in fact best response. D is a best response for that specific value of P. And let's figure this out. What should be the value of P? Well, there are different ways of finding this value. One, you can find this intersection point and this intersection point, and then just randomly pick one P in between these two thresholds. That's one approach. The second approach is, that's the only approach that I have in my mind. So what is the utility of playing D, right? Given that sigma 2 is this guy, P probability X, 1 minus P probability Y. So I erased it for no reason, but let's rewrite it. It's 6P plus 4, 1 minus P. Basically, it's 4 plus 2P. All right? And then what is the expected payoff of playing B instead? Well, it's 3P plus 8, 1 minus P, so it's 8 minus 5P. And then finally, what's the expected payoff of playing C? Well, it's 7P plus 2, 1 minus P, so it's 2 plus 5P. So what I want is the following. I want utility of playing D is higher than utility of playing B, and also utility of C. So that's what I want. 4 plus 2P greater than or equal to 8 minus 5P. Why equal to is fine? Well, because remember, I'm looking for best response. So therefore, equality is fine. It's not dominance. So be careful. So this is one thing. And I also want this, 4 plus payoff, greater than or equal to the expected payoff of playing C, which is 2 plus 5P. So if you simplify this, how so? Well, send P to this left side. So you're going to have 7P greater than or equal to 4. So that means P is greater than or equal to 4 over 7. And then, so this is like slightly less than 0.6. And this, however, implies, if you do the math, 3P is less than or equal to 2, or P is less than or equal to 2 over 3. So you know what? As long as P is less than or equal to 2/3, which is around 0.67, but greater than 4 over 7, which is again around 0.6. So for example, if P is equal to 0.6, all right, I think that's going to work. So if P is equal to 0.6, if you calculate the utility of playing D is going to give 0.6 times 2, 1.2, it's 5.2 utility. And if you calculate this, it's going to be 8 minus 5P, so which is 3, 5 times 0.6. So it's 5, which is less. Very good. So D is giving higher payoff. What about the expected utility of C? Again, 5 times P, which is 3, plus 2, which is 5. Very well. So you know what? When, for example, P is 0.6, we just found that D is the best response to this belief, meaning it gives weakly higher utility than B and D. We didn't look at A. Well, the reason is kind of obvious, because whatever the P value is, remember A is always giving 3 payoff, but D is giving a payoff definitely higher than 3. So therefore, you don't really need to make that comparison. So it's obvious. For that reason, we only compared D with B and C. And what we found is that D is in fact sometimes best response, and hence it should be included in this set, B1. Yep, that's it. So this is basically how we verified that for this example the set of best responses and the set of strategies that are not dominated have to be equal. Once again, it's true for any two-player finite games. Okay?